Okay, so this lecture we start looking at the balance between pressure, force and shear stress in a pressure driven flow. So this is one level more complicated than what we looked at with Couette flow in the previous lecture. So we're going to do that, and we're going to analyse it for a laminar flow, which allows us to do the same kind of things that we did with Couette flow. And we start thinking about what the friction factor is. So this is effectively the wall shear stress, which is related to the pressure drop, and this allows us to work out what this friction factor is that we introduced 2 lectures ago in the steady mechanical energy equation. And that also allows us to talk a little bit more about turbulent boundary layers. And these are really important because turbulent boundary layers generate a lot more pressure drop than laminar boundary layers, and we'd like to try and control this and reduce it if we can as an engineer. Okay, so what we're going to take is a round pipe. It's very long, and we're going to assume it's fully developed. So what that means is nothing is changing in the flow direction except the pressure. And more specifically, the pressure is changing linearly. So effectively the pressure is reducing down the pipe, and there is a pressure gradient, and this pressure gradient is constant. Okay, so we're going to see dP by dx in equations, and we're going to integrate and differentiate, and we're going to treat it as a constant. So even though it looks like a derivative, it actually isn't in this example. And we're going to make use of the bulk mean velocity. So we're not making any assumptions at the moment, so we're not saying whether it's a laminar or a turbulent flow. And whatever the velocity profile is, we know it's not uniform. So we define the bulk mean velocity as the volume flow rate divided by the area. So we could work out the volume flow rate by catching a certain weight of fluid coming out of the pipe for a certain amount of time, and then if we divide that volumetric flow rate by the area, that gives us our average or bulk mean velocity. Okay, so now what we're going to do is do a force balance on a section of our pipe. So it's a section of pipe of length L, and our control volume encompasses all of the fluid in that length L, all the way up to the wall. Okay, and we've got a certain velocity, we've got shear stress on the wall, and we know our pressure between downstream and upstream is different by a certain amount delta P. Okay, so we want to do a force balance in the x direction to work out what the forces are and how the pressure drop is related to the wall shear. Okay, so we've got a force on this surface, and the force is the pressure times the area. The area is pi r squared. Big R is the radius of the pipe, and that force acts in the positive x direction, so we've got a plus here, and we've got the negative x direction, we've got the downstream pressure, and that's pushing in the opposite direction to the coordinate direction, so that gives us a force in the opposite direction, so we have minus P A here, and then we've got the wall shear stress, so this is the wall shear times the area of the pipe surface. So the pipe surface is effectively the curved area of this section, so that's 2 pi r, that gives us the circumference, multiplied by the length, that gives us the curved area, so the curved area times the shear stress gives us the force. Okay, and we can simplify that to the pressure drop per unit length is effectively twice the wall shear divided by the radius. We rearrange this slightly, and this gives us a relationship between the wall shear and the pressure gradient. Okay, and this is a fundamental result. So we haven't made any assumptions here about whether the flow is laminar or turbulent. So this always holds. We're going to make use of this several points in this lecture, so please keep this in mind. So now what we do is we make an assumption. We say we're interested in laminar flow. Okay, so it's not turbulent. So we do the same kind of thing, but we take a slightly different control volume. So it's still length L, but it's of width R. So it doesn't have to go all the way to the wall. It could do. So R can be anything bigger than 0 and up to big R. Okay, so we're doing the same kind of force balance. We've got pressure on here. We're saying we've got the pressure at this bit here, and that's giving us this force. And then we've got that pressure plus the pressure gradient times the length. So this is dx, this length. And remember, the pressure gradient is negative, so this term is less than this, and this gives us a positive total force. And we've got a shear stress resisting this motion. So it's not necessarily the wall shear, but it's a shear stress depending on where R is. Okay, and this 2 pi r dx, that's the size of our control volume when we're doing this in the laminar flow. Okay, and now we make our key assumption, and we say that the shear stress is equal to the viscosity times the velocity gradient. And this is defined as in a Cartesian frame, where y is effectively the distance away from the wall. Okay, so we need to convert this to our cylindrical coordinate system, where r is actually increasing as you're going towards the wall, whereas y is actually getting bigger when you go away from it. So we can relate y to small r using this equation here, and we can work out dy by dr, just minus 1. So we can use the chain rule to convert our fundamental definition for the relationship between shear stress and the velocity gradient in terms of du by dr. So we end up with this. Okay, and then we take this and we can substitute it into this equation up here, and we can get a relationship between the velocity gradient with respect to r and the pressure gradient as a function of r and the liquid viscosity or fluid viscosity. Okay, and once we've got this, we can get the velocity profile, and we'll know everything about our flow. Okay, so we take our equation and we can integrate this with respect to r. So if we integrate this, we end up with an equation that looks like this, and we've got an integration constant, and we can choose the integration constant from a boundary condition, and the obvious boundary condition is to say when r is equal to big R, the velocity is equal to 0, so no slip boundary. Okay, so that's what we say here, and that gives us a value for c. Okay, so effectively c is minus big R squared over 4 times mu times dp by dx. So we put our value for c back in our equation, rearrange it slightly, we end up with something like this, and more traditionally we end up with something that looks like this. Okay, so we can look at this and we can say, okay, so our velocity profile is parabolic. So our velocity should be 0 here, and then it increases very quickly away from the wall, and then it slows and it stops increasing at the center line. Okay, and we can also, now we've got the velocity profile like we did for Couette flow, we can work out the shear stress distribution. So we said our shear stress distribution is this, and therefore our shear stress distribution is effectively this. Okay, and this gives us a linear change in the shear stress. So what this means is that the fluid has lots and lots of stress at the wall, and it reduces and it reduces, and it has 0 at the center line, and it has to have 0 at the center line because of the gradient coming down here and having a right angle at this point. Okay, so the effect of pressure or pressure gradient is to ensure that this linear change in shear stress is present in a pressure driven flow. So this is different from a correct flow. Okay, and we can make sure that our answer is correct because we can recover our general wall shear stress versus pressure drop definition from setting R equal to big R. So my tau becomes the wall stress, and I recover my general relationship that I derived in the previous slide. And there are other things that we can do with this. So we can work out where the maximum velocity is. Obviously it's going to be on the center line, and we can work out what that is. It's just simply this term. And if we wanted to work out the volume flow, we can do that by working out the volume flow in a flow element. So the flow element is an annulus of thickness delta r, width r, and we can say that there is uniform velocity in this little annulus. So the tiny amount of volume flow in that annulus is u times 2 pi r times dr. So this thing is effectively the area. Yeah, and then we can integrate that, and then we have to work out what u is in terms of r, and we can do that because we have the velocity profile up here. So we can take this expression, we can put it in here, we can do the integration, and we can end up working out the volume flow, just like that. So just to sort of point out, the volume flow is a function of r to the 4, so it has a big impact how much volume you can get down a pipe. And if you wanted to relate the bulk mean velocity to the maximum velocity, we can just compare this term with this term, and we can see that the bulk mean velocity is exactly half of the maximum velocity. So the bulk mean velocity is effectively this. Okay. Okay, so that's us looking at laminar flow. Now we're going to start looking at pressure drop and wall shear stress more generally for a turbulent flow. So if we kind of step back a bit and say, well, what would my wall shear stress depend on if we were going to do an experiment? And we might say, well, it depends on the fluid properties, the density and the viscosity. It depends on how much flow you're putting down the pipe. It depends on the pipe diameter. Okay, so we could use the Buckingham pi theorem to work out what our relevant non-dimensional groups are. And when we start looking at this, then, and we do our analysis, we end up working out a non-dimensional wall shear stress. Okay, and this turns out to be our friction factor that we introduced in the steady mechanical energy equation. And it depends on one non-dimensional group, and this non-dimensional group is the Reynolds number. Okay, so if we're going to do an experiment to work out what the pressure drop is on a pipe, effectively what we need to do on the y-axis is we plot F, and on the x-axis we plot the Reynolds number. And then all of our experiments on all our different fluids, all our different diameters, all our different velocities, they will all collapse onto the same graph with the same results. So that's what we're going to do in a minute, but we can already do this for laminar flow. So we don't need to do an experiment for laminar flow because we know what the velocity profile is, and effectively we know what the bulk mean velocity is and the wall shear is. So this allows us to say, right, I can work out that dP by dx is a function of the velocity and the radius and the viscosity, and I can take my expression for dP by dx, I can substitute it into here, and I can work out what F is, my non-dimensional wall shear, is in terms of Reynolds number for a laminar flow, and it ends up being this expression here. So when we start looking at turbulent flow, we find that there's a very different relationship. So and we show this with this slide. So this is our relationship for laminar flow that we've worked out, and this is our fundamental relationship between pressure drop per unit length and the wall shear. And what we can do is we can take our expression for wall shear, which is effectively half rho u squared times 16 over re, and we can put it into this term here. So we end up with something like this, and that looks like pressure drop per unit length as a function of the Reynolds number, the velocity. Okay, and then what we do is we take logs of this equation. So we take a log of this, and we take a log of this, and we can plot it on a curve that has log of the velocity on the x-axis and log of pressure drop per unit length on the y-axis, and we end up with a gradient that's 1, because this is u to the 1 effectively. Okay. So when we do this for a turbulent wall, we don't know what the relationship between the wall shear stress is and the Reynolds number. We have to do an experiment. And so lots of these have been done. And if it's a smooth wall, a classic relationship is the one proposed by Prandtl, and he found that the friction factor is a function of the Reynolds number to minus a quarter. Okay. So we take this term and then we substitute it into here, just as we did for laminar flow, and we end up with something that looks like this, and the pressure drop per unit length is a function of u to the 7 over 4. Okay, and if we take the log of that, we end up plotting another curve, which is this one. And what this shows us is that the pressure drop increases much more quickly in a turbulent flow than it does in a laminar flow. So turbulence has a major effect on pressure drop in pipes, and we would like to try and reduce this and limit it as much as possible. Okay, so how is all of this information made available to engineers? And it's made available using a Moody diagram. So we've got, on the x-axis, we've got the Reynolds number, and it's plotted on a log plot. And we've got, in the y-axis, we've got the friction factor, which is this non-dimensional wall shear stress. Okay, and if it's a laminar flow, so the Reynolds number is less than 2000 or so, then here's our laminar friction factor that we worked out. So we know where this comes from. And the correlation that I showed you for Prandtl's correlation, that's this one down here. So it's he assumes that there's no roughness on the pipe. Okay, so technically what he's assuming is the roughness is small enough, and we'll get onto that a little bit later. So all pipes are rough to some extent, and they are defined in terms of their relative roughness. So this set of numbers corresponds to these lines, and this is the relative roughness. So it's K over D, so K is the roughness and D is the diameter of the pipe. Okay, so when it's really small, when the roughness is really small, we assume it's a smooth pipe, and you have this pressure drop characteristic, and then the roughness can get bigger. And the interesting thing about the Moody diagram is effectively there are 3 zones. So you've got the smooth zone for turbulent flow, which means that the roughness has no effect on the pressure drop. And then we have a zone between the smooth zone and this dotted line where the pipe Reynolds number and the roughness have an effect on the pressure drop or the wall shear stress. Okay, so let's say we choose a roughness of 0.004, and let's say we're in this mixed regime. So if we're on the roughness of 0.04 and we change the Reynolds number, we see that the Reynolds number affects the wall friction. Yeah. And let's say we keep a Reynolds number of 10 to the 5 and we change the roughness, we go vertically, and again we see we generate different pressure drops. And then we have a region out here which is called the fully rough region, and this is quite unusual because as long as the Reynolds number is large enough, it doesn't have any effect on the pressure drop. So, and you can see this because one of these lines in the fully rough region, they're all horizontal. So let's say I'm at a Reynolds number of 10 to the 6 and I've got a roughness of 0.004. So I'm generating this much wall shear and this much pressure drop. So let's say I increase the velocity of my pipe, I put more flow through my pipe, and my Reynolds number increases to 10 to the 7. My pressure drop hasn't risen at all. And if I go to 10 to the 8, again, my pressure drop hasn't risen at all. So this is quite an unusual set of physics, and we need to look at the structure of a turbulent boundary layer to explain this. So the key bit of information is that turbulent boundary layers have a thin region next to the wall where the flow is laminar, and it's called the laminar sublayer. And the thickness of this laminar sublayer depends on the fluid, depends on the viscosity of the fluid, and it depends on the flow velocity. And this is characterized by a Reynolds number that is based on the distance from the wall. So y is 0 at the wall, and y gets bigger as you go away from the wall. Okay, and this symbol is the kinematic viscosity. So this is just the dynamic viscosity divided by density. Okay, and traditionally in fluid textbooks, any non-dimensional wall quantities are given a plus quantity. So in later years, you will see this being defined as y plus. But at the moment, let's just think about it as a Reynolds number, which is what it actually is. So the way to think about this is to say, well, when my Reynolds number is small, what I know about the Reynolds number is that means viscous forces are really important. And when my Reynolds number is really big, it means that inertial forces are important and my flow is going to be turbulent. Okay, so when this y is really small, then my Reynolds number is going to be really small and my flow will be laminar. Yeah, and as I go further away from the wall, my flow gets more and more turbulent, characterized by this increase in the Reynolds number. Okay, so you can see that. So, and what we do is we say, well, when this Reynolds number is 1, that's the division between near the wall it's laminar, and above the wall, above the Reynolds number of 1, it's turbulent. Okay, and you can see that this thickness depends on the velocity. So if you increase the pipe velocity, your thickness of your laminar sublayer is going to get smaller. Yeah. And the key to understanding the Moody diagram is to think about the size of the roughness relative to the thickness of this laminar boundary layer. So the easiest way to do it is to think about the two limits. So when it's a smooth wall, the roughness is smaller than the, or is smaller than the thickness of the laminar sublayer. Okay, so the thickness is kind of, the roughness is hidden in this laminar sublayer, and the flow doesn't see it effectively, and it doesn't affect the pressure drop. Okay, and the turbulence out here is driven by what's coming into the pipe and the state of the flow. It's not actually driven by the roughness itself. Okay, and then you take the opposite case when it's the fully rough case, and your roughness elements are much larger than the laminar sublayer. So your roughness elements are kind of protruding into the turbulent flow. They're not in the laminar region anymore. And because they're in the turbulent region, you start getting vortices shed off these roughness elements, and these roughness elements and these vortices that are shed actually go and create the turbulence. Yeah, and so this means that the roughness elements are generating the turbulence, not the flow. And this is why the pressure drop for fully rough walls only depends on the roughness, and it doesn't depend on the Reynolds number. Okay, so and this is what I want you to appreciate from the Moody diagram, and how these regimes are different. Okay, so we've covered quite a lot here. We've covered how what the wall shear stress is and the flow velocities for laminar flow in a pipe where you've got a pressure gradient. We've defined the coefficient of friction for a laminar flow. We've talked about the Moody diagram, which has more information now, and we've talked very briefly about some of the structures of a turbulent boundary layer and why the roughness is really important when you're starting to think about pressure drop. Okay, thank you.